Cams on everyone, let's start off. So this was the lesson that we did, a rough bank road. Like I said, this itself is a question and also the theory. So basically you do banking because you don't want to depend completely on friction, in order to make you go in a circle. So in case of a bank road, the normal reaction would actually help you to go in a circle and the friction becomes a bonus. So yeah, let's go ahead with 3 more questions. Now see, let's do one question of something else and then we'll go ahead. Let's say we have a rod here, which is going with omega. This is fixed. Let's say we have a point A here at a distance L from here. And we have a point B here at a distance of, let's call it R. And this whole setup is rotating with omega. Okay. This is the top view. It doesn't matter actually. So this is there. So let me ask you a few things. Find velocity of A of B with respect to A. Find acceleration of B with respect to A. Find centrifugal force on B as seen by A. So my observer is A. Let's assume B is small block or something, getting it? And centrifugal force of B as seen by A. Find pseudo force on B as seen by A. Mass of A, let it be MA, and mass of B, let it be MB. If you remember last time, you had that all that discussion, right? Rotation and stuff. It's based on that. Let's try to do this thing. This will make things more clear. The first one is something a little different. Take a minute, then I'll explain all those things. Others, do keep your cams on. So let me help with a few things here. Now, if you go back to the derivation there, so when I taught you that, there is something more we can do that. Look at this part that we got. If you look at this part, this actually had two terms. If you remember this, I think I should write the page number also. It's page 44. So listen carefully here. So this is something which we have not done before because till now we never dealt with rotations. So there are two things that are happening here. One, if you look at the velocity here, so whenever you say velocity of B with respect to A, there are actually two relative velocities. Velocity of B with respect to A, the translational component. That's your first part. The second thing, R omega, is your tangential velocity of B with respect to A, the rotational component. What do you mean by that? The thing is, till now what we studied was only this part, which was VB minus VA directly. You subtracted the velocities and your job was done. So what was happening is, think of like this. Look at the screen in front of you, right? If you're looking at the screen in front of you, if you just turn your head towards right, don't you think the screen is going to the left? You're getting this? Even without you moving, if you just turn your head, you think the screen is going back. So there are actually two things happening here. See, if you have a person who is running with, let's say, 10 meters per second, and if you look at this point here, he thinks this point is going back. Similarly, if you look at a person here, and let me say this is your head with the eyes. So if you turn your head with omega, so when you're turning your head with omega, you think this point, whatever is it, let's call it some point P. Let this distance be L. So this person will think the point P is going down with L omega. Basically, this is the relative velocity because of turning your head. This is the relative velocity of P due to the rotation of the observer. So whenever this guy rotates this way with omega, he thinks P is going downward with L omega. Is that making sense? This is your rotational relative velocity. Same thing, look at this thing. Suppose if this man is running with speed V and P is at rest, what will this person think? He will think P is going back with V. So if you keep the observer here, this is your relative velocity due to translation. This is what we studied in kinematics. This is your relative velocity due to translation. So think of like this, huh? Suppose, let's say, if you take a big wheel and let's say you're standing like this. So let's say you're standing like this. How do I keep your face in this? I'll assume your face is like this, okay? I'm putting like a triangle. So you're looking in this direction. And let's say there is something here. This point, let's call it B here, and let's call this thing A here. Now tell me one thing. If let's say A is not rotating, what would have happened? After some time, if A is not rotating, A would come like this, isn't it? This is translation. or let me ask you the other way around. When both of them rotate, now tell me one thing. If you ask A, what happened to B, what will A tell about B? Does A ever think B is moving? A will always think B is in front of me, isn't it? A always thinks B is in front of me. It will think B is never moving. But if you try to use your relative velocity, let this distance be L, and this distance is R. A ka velocity is L omega, the tangential velocity. B ka velocity is R omega. So if you try to use the relative velocity B with respect to A, you'll end up with R omega minus L omega. This is not equal to 0. You're getting the problem there? A will always think B is in front of me, means I will think it is not moving. But if you try to use the relative velocity, you're not getting it 0. That's because you're forgetting one more component. Is this making sense, everyone? There are actually two relative velocities. One relative velocity will come because you're moving. Another relative velocity will come because you're turning your head. Is that sentence making sense? Now coming back to the question. So this is the main thing that you should have an idea. So if you look at this example, the question which we have. So there are two things happening here. Your observer A is not only going with speed V, which is L omega. B is going with R omega. So this is V B with respect to A. This is your translational relative velocity, which we studied in kinematics. This will be R omega minus L omega J cap. That means this observer will think this point B is going with R omega minus L omega. So if you bring him to rest. The second part, because A himself is rotating, if you ask A what is happening to B, he will say, okay, my head is rotating with omega, because of which I think B is going down. And what is the distance between us? The distance between is R minus L. So he thinks B is going down with R minus L omega. This is your velocity of B with respect to A due to rotation. This is happening because your head is rotating. Till now, we never encountered this because we never cared about rotation. We simply thought particles are going in a line. So now if you combine both of them, velocity of B with respect to A, so the translation is R minus L omega J cap. And this will be minus R minus L omega J cap. We get 0. And it kind of makes sense because A will always think B is never moving. He will think B is always in front of me, isn't it? Think about it. If you and I are sitting in a merry-go-round, you're sitting in front of me. Do I ever think you're moving? If I forget about rotation and everything, I will always think you're in front of me. So in this question, if you ask A, boss, what is the velocity of B? He will say it is 0. It is not moving only. Are you clear with this? The problem why you won't get an answer if you directly do R omega minus L omega is because we are missing a point. There are two relative velocities. One is coming because of translation and one is coming because of rotation. Rotation we never considered because till now all we did was translation. Is this concept clear, everyone? And what about acceleration? Same story. Since I think, A thinks B is at rest, that means there is no acceleration also. A thinks B is at rest. Therefore, velocity of A with velocity of B with respect to A is 0. Acceleration of B with respect to A is also 0. If it doesn't move, then where are you getting velocity and acceleration from? Both the answers are 0 for the first two cases. Clear with this? Like I said, these are the theoretical type of questions. So you should exactly know what are you talking about, velocity, translation, and everything. Any doubts on this? But is that making sense? If you rotate your head, if you're just sitting and looking at your screen, and if you rotate your head, don't you think the screen is going back? So you rotating your head does affect the motion of relative motion of the other objects. So you have to include that. What about the third part? This I told you. Centrifugal force is different, pseudo force is different. So for the C and D, so if you ask A to calculate the centrifugal force, What is centrifugal force? M omega square R. R is the distance between you and me, the observer and the object. So this is A, this is B. The distance between them is R minus L. The centrifugal force will be mass of B omega square R minus L. This is your centrifugal force. Straightforward. M omega square R is not the centrifugal force. Do you remember how we did that? If you keep the observer on the hinge, your life would have been easy. Second thing, this guy also, he himself is going in a circle. So he has his own centripetal acceleration, a centripetal, which is omega square L. This is your centripetal acceleration. So now if you ask him, how many forces are there on B? He will say there are actually two pseudo forces, which is mb omega square R minus L. This is your centrifugal force. And because I am myself is accelerating, this is a linear acceleration, there'll be one more pseudo force, which is mb omega square L. This is the pseudo force due to the linear acceleration. Again, if you go back to this derivation, this comes because of your this first term here. This is a pseudo force due to your linear acceleration. This is the examples I gave you, if you remember. If you're accelerating, then there'll be a linear pseudo force. This is the pseudo force due to that A centripetal. So what is the total pseudo force? The combination of these two. So the total pseudo force will be mb omega square R. And if you remember, this is what I told you. So if you're solving problems, keep the observer on the hinge, keep your life easy. Don't take observer wherever you want. Things will get unnecessarily messed up. So no matter where you stand, the total pseudo force on B is same. Whether you stand at point A or whether you stand on the hinge, you stand anywhere, the total pseudo force will be same. Centrifugal force will change. The pseudo force due to this linear acceleration will change, but the total pseudo force will remain same. Is this making sense? I know it can look a little confusing, but again, I'm telling you, after the class gets over, just go through this stuff, right? Go through these three examples, the centrifugal force, this example, B example, C example, and the question which we did today. All this together is one chunk. Is this making sense? Centrifugal force is different from total pseudo force. Centrifugal force is part of a pseudo force. Clear? Any doubts on this? Anyone confused with anything here, please ask me. Okay, let's go ahead. So simple question, huh? Same thing if I ask you like this. What if an observer is standing somewhere here? If you ask him what is the pseudo force, what will he say? M omega square R. You're getting it? It doesn't matter where you keep. Total pseudo force is M omega square R. Another way to explain that, think of like this. If you look at B, we know on B, there is a centripetal force, which is M omega square R. And in a rotating frame, no matter where you stand, you think it is at rest. That means in order to cancel this, we need one more force, which is nothing but pseudo force, which must be also equal to M omega square R. Is that making sense? So no matter in which frame you stand, the total pseudo force is M omega square R. The centrifugal force keeps changing. So make sure to go through this, right? You will understand most of it. You'll still get confused. Do ask in the next class, get it cleared. That is okay. Let's see one more. That's the thing I didn't show you that in the last class, because last class you already got confused with so many things. So I'm just introducing little every class so that you can absorb it slowly. Now, Let's see the next thing. So someone built a bowl shape marble track. So we have a smooth marble racetrack. So this was a story I heard, in Europe now, they hired a designer or an architect, to build a racetrack for this NASCAR or Formula racing kind of thing. So this guy built a track in some proper way, in some weird way, with some particular curve and all. And then what they noticed, right, when they started test driving on the track, they noticed no matter how fast you go, the time taken for one revolution is same. Matlab, you take your car, go at 100, you take your car, go at 120, you take your car, go at 180, the time taken to come back in one trip is same. Now, such a racetrack is useless, isn't it? Means all are going to get the first place. It's pretty weird. So something weird happened. Okay? So we have something of that sort. So you made a bowl here. This is X. This is Y. Right? It is observed. A marble thrown with any speed. This is not a spherical bowl. A marble thrown with any speed completes one revolution in time t. Now you need to think why the hell is that happening? So happens, when you're architect and when you're designing, some weird things happen sometimes. So that means if you take a ball and if you throw it speed v1, it goes in a circle like this. If you throw faster, it actually goes in a different path. They all don't go in the same track. There is a catch. It goes like this. So the faster you throw, the bigger the circle. Slower you throw, smaller the circle. So for different speeds, they take same time. So if I throw with v2, which is greater than v1, it goes in a bigger circle. Speed is more, circle ka length is more, but the time is same. So what I want you to find, I want you to find this equation of the track. So what is this curve ka equation? Find the equation of the track. Is the scenario clear? How the hell it is happening, that's a different story. But is the story clear? So you made a bowl. It's not a spherical bowl. I don't know what is that equation. It can be anything. So when you throw this balls inside with any speed, you observe they always complete the circle in one same time period. Yeah, they go in different circles, but they'll complete one revolution in same time period. Then what is the equation of that bowl? Try. I'll give you 2 minutes. Anyone not clear with the picture, please ask me. And others do keep your cams on. Let's see. Omega square x square. Right, Siddesh. We have one answer. Sir, what is our answer? Yeah. That's a weird equation we got. Okay. Another 30-40 seconds. You got a straight line, Rajati. So what you got was something like this. Nay, nothing wrong could be, but that's not the answer. You made a cone basically. I know what you did. You did everything, then you goofed up something. You wrote tan theta is y by x instead of writing dy by dx. I think so. Maybe that could be the mistake. Let's see. Others can keep trying. It'll take me another minute or two to explain the whole thing and start solving anyways. So when you take this bowl, now again, remember, it looks like a circle. It is not. I'm unable to draw it properly. So if you take marble at any x and y coordinate, x comma y, this is going in this circle. What are the forces acting on this? mg, your centrifugal force, m omega square x. At this point, this is your tangent. This is your theta. This is your normal. There, these are the three forces acting on this. Now, if you look at the components, if that is theta, this is theta, this is also theta. So on the tangent here, if you look at the forces, we have m omega square x cos theta. We have m omega square x sine theta. We have your normal reaction. We have mg sine theta. And we have mg cos theta. This is how you divide the forces. I'm more interested in the forces along the line tangent. So you get m omega square x cos theta is equal to mg sine theta. Cancels. You end up with tan theta is equal to omega square x by g. We remember tan theta is nothing but slope of a tangent. That's the definition. That's how we started the whole differentiation from. Slope of the tangent is tan theta, which is nothing but dy by dx. So we got a dy by dx is equal to omega square x by g. So this will be dy is equal to omega square by g x dx. Limits 0 to x and 0 to y. Because we are taking the bottom as origin. So this will be y is equal to x dx is x square by 2. This is the equation and this is a parabola, everyone. You know what shape is this? This is a paraboloid. This is a paraboloid. And in case you forgot, this is something we did in calculus. This shape. So when you actually take a bucket of water and spin it, the shape which you get is the paraboloid. So in this bowl, right, if you make a bowl of a paraboloid shape and if you throw a ball inside, it takes same time to complete one revolution. So this was a paraboloid. And what is omega? Yeah, omega is nothing but the time period. So time period t will be nothing but angle, which is 2 pi by angular velocity omega. So there you got omega from there, you can substitute, you'll get the answer in terms of t. Check, that's your equation. I think, yeah, Hutsa, you got it. Ovia got it. Arya got it, yeah. All clear with this? So the bowl is actually a paraboloid shape. Any doubts on the steps? Yeah. Next thing. Clear, na, Vanshika? Sudiksha, Shaurya, Srihari.
Sir, how did you apply an NLM, sir?
How did I apply NLM? What do you mean by that?
सर कि उस पॉइंट में आपने m ओमेगा स्क्वायर x को ये इक्विलिब्रियम में लिया है.
Yeah, because it is just going in this circle, no? It is not going up and down. It is not going this way. It is in that direction. There's no force.
Okay, sir.
It is maintaining a horizontal circle, right? Is it going up and down? No, na. So that way. Next thing. Again, this is a little bit of a theory there. Variation of G due to Earth's rotation. Now, this is exactly not the variation of G, but you start feeling, the gravity is changing because of the Earth rotation. So again, tell me one thing, what is up and down? We discussed this in kinematics. Anyone remembers? What is up and down? If you say like this up and this is down, we have a problem. That means people on the North Pole are standing like this. People in the South Pole are walking with their heads. And people on the equator are crawling on the floors. So what's exactly up and down then? So toward the center of the Earth is down and away from the center of the Earth is up. So when you take the Earth rotation, again assuming it's passing through the center omega. So whenever you're standing on the Earth, you're actually standing like this. Your legs are pointing toward the center of the Earth approximately. And you're going in a circle like this. So all the people on the Earth are not going in similar radius. We are going in different circles. So now what are the forces acting on this? The forces acting on this will be a normal reaction. Your own weight mg. Now remember, mg will be towards the center. Don't put down. Down here is towards the center. And since you're going in a circle, there'll be a centrifugal force, which is m omega square smaller, where smaller is the radius of this circle. So here we take this angle as theta. This angle is called co-latitude angle. So basically at equator theta is 0 and North Pole theta is 90. That's your latitude angle. So this angle also will be theta. So if you look at the forces on this person, and remember here, this radius of the circle is capital R. So we get R cos theta is equal to small r. So if you draw the FPD of this man, this will be m omega square r cos theta, m omega square r sin theta, your own weight mg, and your normal reaction n. So you get normal reaction n is equal to n minus m omega square r cos theta. This will be equal to, remember, this is what you think is gravity. In reality, what you're experiencing is not pure gravity. You're also experiencing some kind of centrifugal force. And G apparent. Mm will cancel. You end up with G minus omega square. But what is small r? Which is r cos square theta. Is G apparent. So I'll just put it there. This is r cos theta. You can take this r from here and substitute here. There. So you get a G apparent G minus omega square r cos square theta. We will do this again in gravitation, but yeah, a little idea there. So everywhere on the Earth's surface, the gravity is not uniform. That means if you can rotate this pretty fast, you can, let's say, they can ask a question like this: what should be the rotation of the Earth omega so that people on the equator start flying off? Matlab, they start thinking there is no gravity. But have a look at this. I'll show you that on the next page. So this is theta 0 and this is theta 90. So if you can clearly see the equation, so at the equator, you actually feel gravity slightly less than at poles. That is the reason whenever you're launching rockets, right, people prefer to launch closer to the equator, because you have to go against less gravity. And did you ever think about this? Let's say if humans are going to travel in space, what's the biggest problem we face? There are actually multiple problems. One of the major problems that we face, right? Our human bodies, right, are designed to work in gravity. Once you put a human in a gravity-free space, things get pretty bad pretty fast. So one of the major problem is this. If you look at a human body, right, arteries and veins, the arteries and veins in the legs are actually thinner compared to the arteries and veins in the upper part of the body. That is because, did you ever play with your water tap? If you close the water tap thing, what will happen? Let's say if you have a water tap, if you close half of the area, what happens to the speed of the water? It goes faster. So what happens is the arteries and veins in the lower part of your legs, right, are thinner. Since the arteries are thinner, the blood which is flowing goes faster, so that the blood can reach from your legs to your heart, because the blood has to flow against gravity. Now, once you go into the gravity-free space, what will happen? There is no gravity, but the blood is still flowing faster towards your head. So blood starts accumulating on the upper part of the body near the head. Now the brain will start thinking the body is producing too much blood, and it stops producing RBC. You actually become anemic. That is one. Second thing, even though you don't do any exercise on the earth, at every instant your body is being pulled down by gravity. So your muscles are actually working day in and day out, 24/7, even though you don't do any exercise. So you're actually maintaining a certain muscle mass. Muscle is more expensive. It takes more energy to maintain than fat. So, but it is required, the body will maintain. But once I put you in a gravity-free space, there is no need to use your muscles. You're simply floating. Your entire muscles will degenerate in a month. So in a spaceship, if you see astronauts, right, every day they have to exercise for 4 hours just to maintain the muscle mass. Just to be normal like us, every day they have to exercise for 4 hours. Getting it? So if you're launching a spaceship from Earth to some other planet and the journey is going to take 4 or 5 years, people will die inside. Even before reaching the planet, they will die of health complications. Anyone saw this movie, WALL-E? That robot is there on the Earth, it is cleaning things and all. If anyone remembers that movie, right, you should see that scene, where the humans are in a spaceship outside the Earth. They're waiting for the Earth to be cleaned. If you look at the humans now, all become pretty fat and everything, and no one can walk. All are being carried on, small shuttles in and out. No one can walk. They become so unhealthy. So one of the problem of space travel, yeah, that you also have a lot of other stuff, but human bodies, right, we can't live in space without gravity. So how do you design a spaceship, right? If you're going into space for long journeys, let's say you have to travel for 20 years or 30 years, or let's say even 200 years. If you're traveling for 200 years, then you have to create a spaceship where you put people inside, couples, right, families. So they live in that spaceship for 200 years. After 200 years, maybe fifth or sixth generation will land on the planet. That is how you can send humans with the current technology. You can't send them within one lifetime. So how do you think we can create gravity? Unfortunately, we can't create gravity so far. We don't have the tech. People are searching for a particle called graviton, which we don't have yet. It's a hypothetical thing. So one way to do this is, first time I saw this, I got this idea from Tom and Jerry. So this is how we construct a spaceship. You construct your spaceship in the form of a big cylinder. And this cylinder will be rotating with omega, where this omega square r, so you want to create gravity, right? M omega square r must be equal to mg. So omega must be root over g by r. So if you take a big cylinder and rotate with this omega, everyone on this cylinder will experience a centrifugal force away from the center. So people will think there is a gravity, which is m omega square r, away from the center. You getting this? So in this rotating cylinder, how will the world be? If you're constructing buildings, the buildings will look like this. Yeah. And if you're walking in this world, you'll be walking on a curve. And suppose if you and I are living on this planet in this cylinder, you'll be standing like this here. So I can look up and say hi. And you're looking down and saying hi. This is how people will live on this kind of a cylinder. So here, what is up and down? Here, towards the center is up. This is down. So we can't create gravity, but we can create centrifugal force, which behaves like gravity. So we have a rotating cylinder, and if you put people inside, and this is how you can survive for a long time. There are no side effects because human bodies can't figure out between centrifugal force and gravitation. Is that clear, everyone? And if you have seen Interstellar movie, actually you will find this thing. I'm pretty sure you skipped it. Everyone must be. Yeah, they do have spin, but maintaining this for a long time. You're talking about long journeys. But the cylinder has to be also pretty big, right? I'm pretty sure everyone saw that Interstellar and people are busy watching the black hole. And they missed this scene.
Mr. Cooper.
I hope everyone has seen the movie, right? So this is the climax scene, this guy just wakes up.
Slow, sir. Nice and easy, Mr. Cooper.
Yeah, volume is less.
Remember, you're no spring chicken anymore. Actually, you are 124 years old.
So, something happened in the story. He gets saved and everything.
Lucky.
So that guy gets up from the hospital.
With only minutes left in your oxygen supply.
Look at this scene. He looks outside. People are playing baseball. Great. They hit the ball. And there. Can you see that? Can you see how the world is? It's actually a huge cylinder which is rotating. And see how the ball goes. Can you see how the houses are? They're inverted. And did you see how the ball traveled? It traveled in a curve.
Where am
I don't think you get to see the full cylinder, I guess.
Currently orbiting Saturn. Cooper Station. What nice you to name it after me. What?
There you can see slightly here, it is a curve outside.
Well, the station.
I don't think they'll show the full cylinder, but again, look at that scene again when they hit the ball. Hits the ball. There, look at that surface. Oh, yeah, it's went too fast. There, and it's inverted. They show it later. Actually, if you see the whole movie, I think you will get to see. Here, you can see this thing. There, it is there. This guy comes out for a walk, and can you see? You can't tell any difference. It looks like normal Earth only. The cylinder is pretty big.
It was perfect.
There. Can you see the cylinder behind? Basically, this is a rotating cylinder. You literally have farms, you have houses, and you have everything there. And the sunlight, they're getting it from that cylindrical thing there. There you can clearly see the cylinder. And this is how you construct a spaceship in the future if you want people to travel. You can't create gravity. This is what you do.
Of course, I didn't.
And there, look at that curve there. Such a huge one.
Personally.
Plate upside down, glasses or cups, whatever it was upside down.
Oh my, that was a farmer.
Yep, next time you see the movie, now you can see that.
Sir, even in the
This is the
movie
problem
Martian,
with
they
physics.
showed the
You go to a
whole
movie,
thing.
Instead of seeing the movie, you start finding physics. It's a good movie though. Right, it's like a hamster cycle. It's basically that big cylinder there which is rotating. Clear, everyone? So that is how you get that cylinder there, and yeah, and if you want to make this So on Earth, if you want to make G 0 at the equator, this is mg and this is m omega square r. So you get the same equation basically. So if you take mg is equal to m omega square r, so if the Earth rotates with this speed, which is g by r, right? So on equator, it feels like there's no gravity. So you literally start floating at equator. This will be a CET or a mains level question. Yeah. They literally in that movie, they hired PhD people to recreate everything. They actually bring science people to ask, like, is the story making sense or not? Not like a Salman Khan movie where he takes a machine gun and starts shooting 200 people up and down. So you don't ask logics in our movies. ठीक है ना? The thing is that I think it is not like all English movies are also great. There are some hopeless movies also. Movies are like that. Therefore, some are made for entertainment. Some are actually to kindle that interest. Like wow, something is there. Some are just hopeless comedy movies. Can't do anything about it. That's also fine. Clear with this? Then let's go ahead more. Next thing. So till now we handled uniform circular motion. So what happens if the thing also starts speeding up? Non-uniform circular motion. Now in a non-uniform circular motion, the speed of the particle is not constant. The speed of the particle is not constant. Right? Therefore, now the particle will have actually two accelerations. The particle has centripetal acceleration, which is responsible to make you go in a circle. If you remember, that's what the centripetal acceleration does, right? Every time it brings you in and your velocity puts you back. So that story is still the same. So there are two accelerations which will play the game now. One is responsible to make you go in a circle. So you still have your centripetal acceleration, which is responsible for making it go in a circle. And now you'll also have so basically this guy changes direction. That's what centripetal acceleration does. It changes your direction of velocity. And also now you have tangential acceleration, which is responsible for changing speed. So A tangential will be rate of change of your tangential speed. Again, remember, you're still going in a circle, so the other accelerations won't come. This can be also written as V tangential, dV tangential by ds. You can use your regular kinematics. And remember, A tangential is also equal to R alpha. Alpha is your angular acceleration. And S is your tangential distance. So that's the distance along the circumference. That means now when particle goes on a circle, it will actually start experiencing two accelerations. One, you have your centripetal acceleration. Another, you have your A tangential. A centripetal, A tangential. Something of this sort. I'll write that. And the resultant of these two will be something like this. This is your A net. There, now your acceleration won't be towards the center. So if they ask you find the net acceleration, it is a resultant of centripetal square plus A tangential square. Yeah, have a look at this. Let me show you with an example. That's it. So technically, this is the only new thing. So in a non-uniform circular motion, you'll have an additional acceleration called A tangential, which is responsible to change your speed. Other than that, everything looks same. Clear, everyone? So let me take an example. You can do it as a question or an example. So consider a vehicle goes in a circle of radius r, starting from rest. With acceleration A. The constant tangential acceleration. So questions would be like this. Find the speed. Find A centripetal. Find A net. Find the frictional force. At time t. They would ask you something of this sort. So let me show you how to do one. So this is the picture. So we have a circle, top view. So we have a vehicle here whose speed is 0, and you have an acceleration A tangential is A. So this guy starts going in a circle with increasing speed. Since A is constant, I can use my kinematics equations. V is equal to U plus AT. I'll get V is equal to AT. Centripetal acceleration is V square by R. This will be A square T square by R. Net acceleration will be root over A centripetal square plus A tangential square. That will be root over A power 4 T power 4 by R square plus A tangential is A square. That's your net acceleration. Now, if you actually look at the acceleration ka picture, any doubts on this page? Any doubts so far? Tanishka, clear with this? Shreyan? Advai? Aditi? Then, yeah. So now if I see this actually in a circle, see this is how the acceleration is changing. So at t is equal to 0, you don't have any speed. So you have only A tangential. After some time, your speed is increasing. So A tangential, you will also have an A centripetal. So initially A centripetal is 0 because you don't have any speed. Your speed is some V. This will be the net acceleration. If you leave for some time, your speed will increase even more. But remember, A tangential will be same. But this time your A centripetal will become bigger. And your net acceleration also will change. Again, if you leave for some more time, you will go even faster. A tangential ka length will remain same, but your A centripetal keeps becoming bigger and bigger. This will be your A net. This is how the picture will keep changing. Because if you remember, A centripetal is V square by R. As speed increases, A centripetal increases. This is how the acceleration would look like. And because of this, if you look at A net also increases in magnitude. And if you actually try to find this angle, where if I take this angle to be theta, you will get tan theta, opposite side, which is A centripetal by A tangential. Theta is the angle between net acceleration and velocity. This is the velocity, this is the velocity. Theta is the angle between A net and velocity vector. So theta is also not constant, it is changing continuously. Now the question comes, if you're going in this circle with this acceleration, who is providing this acceleration? Someone has to provide this acceleration. So this A net is provided by friction. Meaning if you're going on a horizontal rough road, A net is provided by, let me show that in the next page. A net is provided by friction. So you will have friction in the direction of A net. And look at this, the friction is also increasing in magnitude. But unfortunately, friction has a limit. So friction will be mass into A net. But we know friction must be less than equal to mu into N. So this will be M into A net, which is A centripetal square plus A tangential square is less than equal to mu mg. This will be A square T square by R power 4. We calculated this just now. Plus A square will be less than equal to mu g. If you square it on both sides, you will end up with T square is a T power 4, I guess that is, yeah. We get T power 4 will be mu g minus A square R square by A power 4 to the power of 1 by 4. So up to this time, it won't slip. So I can ask you a lot of questions. Find the time when the block slips. So block does not slip this till this time. So look at the story there. If you want to go in a circle, you need centripetal acceleration. And if your speed is increasing, you need tangential acceleration. Who is providing all these accelerations? There is only one guy to provide all this, friction. Now your A tangential is constant, great. But your A centripetal is the problem. Your A centripetal is continuously increasing. That means you're asking friction for more and more force as time passes. And friction will say, boss, I can give you up to mu mg. Once you exceed that value, it can't provide anymore. So if you're going in a car like this is what you will notice. So for the initial time, there'll be no problem. Your friction is providing. At some point, you'll exceed the speed. You'll start spiraling in. This is what will happen. You'll start skidding outside. Because friction cannot provide the required centripetal force and the acceleration, it will skid outside. This is the reason when you're going on a cycle and you're taking a turn, you don't pedal your cycle. Ever observed that? You do it instinctively. When you're taking a turn, actually you slow down. You don't pedal fast and go into a turn. Is this clear, everyone? Any doubts on this? This is an example. This is a problem. This is a theory. Like this is how you handle non-uniform circular motion. Again, look at the steps what I did. First, I found the speed that comes from kinematics. Then I found A centripetal that comes from V square by R. If you take the resultant of these two, I'll get A net. Who provides this A net? Friction. So F is M A net. And what is the angle between them? Opposite side by edge is N side. So AC by AT. Any doubts on the steps? Clear this? Take a break. Come back by 9:39. We'll continue from here. Any doubts so far? Chalo, come back in 5 minutes then. Yeah, let's start off. Let's see a question. Are the scans on? Same thing, particle is going in a circle. Let's say we have radius is 10 meters. We have a body here, mass of 2 kg, which is going with an acceleration a is equal to t. There, so you have a variable acceleration. A vehicle goes in a circle of radius 10 meters with tangential acceleration a is equal to t. T is time. Starting from rest. Find speed. A centripetal. A net. Friction. And angle between A net and V bar at time t. The same thing what I taught you, but I just made A is equal to t, instead of constant. Let's get them all. Try. Everyone should try. Just straightforward. It looks complex and all, but you just get the velocity and put everything, you'll get the answers. Is t cube by 6 near Siddhesh. Let's see. Yeah, I think most of you got it. Numbers are bad. First thing, you're having acceleration A is equal to T. A is dv by dt. dv is t dt. You're starting with 0 speed, so this is 0 to t. V is equal to t square by 2. Once you got that, then your A centripetal is simply V square by R. V is nothing but t square, so that will be t power 4 by 4R. R is 10, you can substitute the values. A tangential is t given anyway. A net will be root over A centripetal square plus AT square. Who is providing this acceleration? Friction. So that is F is equal to ma net. What about the angle? So at any time, we have your A tangential this way and you have your A centripetal this way. This is your A net. This is your theta. Tan theta will be A centripetal by AT, and which you know both of them, you can substitute here. So t power 4 by 4R by t, that's t cube by 3R. Okay, I think someone typed this answer. You're giving for acceleration. Check it out. Clear with this? That's it. So non-uniform, there's nothing really out of the world, but this is how you do it. But let's see a few more variations. Any doubts on this? Let's see one more. This next one was a PYQ. It's an old one. Kinetic energy of a particle going in a circle of radius r is given by k is equal to b into s square. K is your kinetic energy. B is a constant. S is the tangential distance traveled. So the more you travel on the circle, you get more kinetic energy. And I hope you know what is kinetic energy, half mv square. Find the net acceleration as function of s. Mass of the particle is m.
So does the particle start from rest?
Come again.
So does the particle start from rest?
It doesn't matter. Does it matter?
Yes, sir.
It doesn't matter. Problem क्या होगा ना? If it starts from rest, then initial kinetic energy is 0.
Okay. Yeah, right.
I don't know, man. I don't think you need it though.
While putting limits, we need.
Integration है ही नहीं रे कहीं पे. Siddesh got something big. Okay. Let's see. What is this? Kinetic energy. So kinetic energy is equal to Bs square. So kinetic energy is nothing but half mv square. So from here indirectly I got v square, which is 2b s square by m. Great, because if I know v square, I can find my centripetal acceleration. V square by r, which is, did I give the radius? I gave. So that would be 2bs square by mr. So half of the job is done. So if I know A tangential, my jobs will be done. That I think I can find. So differentiate with s. If you differentiate with respect to s, v square ka differential will be 2v dv by ds. This will be 2v by m, and s square ka differential is 2s. So, and we know v dv by ds is nothing but acceleration. So v dv by ds will be 2bs by m. This is your A tangential, everyone. You're done. So you know A tangential, you know A centripetal. So A net will be root over A centripetal square plus A tangential square. That would be 4b square s power 4 by m square r square plus 4b square s square by m square. Have a look at this. All got this? You can take out that 2b by m r common and all. You can simplify, but there. You get questions of this sort. This was a PYQ. Clear? Let's see one more. Any doubts on this? Anyone not clear with anything particular here? Please ask. Shaurya, Pratyasha? Clear, na? Rudransh? Devanshi? Clear with this? Advait? Aditi? Great. Let's see one more. We have a big ring here. Here we have a ring. So this ring of mass m, which can slide freely. And this is a smooth circular frame. So basically this ring can slide on this smooth circular frame. This is a vertical ring, so there is a gravity. And then what you did, you also connected this. This is your diameter. This is your center. So from here, you connected a spring to the ring. The spring constant is K. This angle is 120 degrees. And at this instant, the ring is also traveling with speed v. The natural length of the spring is r. Right? Initially, the bead is moving with speed v at this time.
So this is a vertical frame, right?
This is a vertical frame. मतलब this is the frontal view. देखा ना gravity दिया ना यहाँ पे.
Yes.
So you're seeing this in the front. मतलब look at your clock on a wall. It's like a clock. It is in front of you. मतलब the gravity mg will act on the ring like this. It is trying to pull it down. Initially the speed is v. So find a centripetal, a tangential, and normal reaction at this instant. There, let's get this. What is step 1? Draw the FBD. Start from there.
Sir, here we are asked to find A tangential and A centripetal, that is with respect to the center of the circle or the point where spring is attached.
A centripetal मतलब ground frame god. Centrifugal force नहीं पूछा मैंने, centripetal acceleration.
So like we have to the center we are taking for centripetal, that is the point on the where the string is attached or the center of the frame.
No, forget about the spring and all. The ring is going in what? Ring is going in a circle.
Yes.
Bus.
Okay, so just consider the center.
No, it is still going in a circle, right? Who is pulling from where you are pulling? Why do I care?
No, because like centripetal and tangential can also be defined for the spring as the center.
But I gave you a circle can go only in a circle na frame na re.
Okay, sir.
ठीक है, I know what you're saying. The net acceleration will be same no matter which frame you take. I got your point, what you're trying to say, but yeah. Yeah, answer will come in terms of K, M, G, R. There are a lot of variables. First of all, can you tell me one thing, is the spring in natural length? The natural length is R. First of all, you need to find this length. From there, you'll get the elongation. I think numbers are bad. Just get me the equations and leave it. Numbers are bad. Now I get your point, Arya, but see, nothing is mentioned now. And if something is going in a circle, always treat the center only. Don't take all, they will mention what you're asking. They will tell you specifically, nothing is called center of the circle. Keep it simple. Because see, the problem with this point, if you start taking this point, now we'll also have a radial velocity along this direction. We don't want to get into all that. So
No, I meant like d theta by dt for the center will be twice that of for the point on the frame.
that will be for omega, no?
Yeah.
Did you guys find the elongation in the spring? How much is the elongation? Let's use some geometry. So this is 120 degrees. This is R. This is R. So from here, if you drop a perpendicular, this will be 60 degrees and this will be 60 degrees. So this will be R sine 60. And this will be R sine 60. So the length of the spring at this instant is 2R sine 60. Which is R root 3. And what is the elongation? The current length R root 3 and the initial length was R. This is your elongation, everyone. The numbers are bad. I should have given maybe, I don't know what can I give to get good numbers, but okay. So r root 3 minus 1. So the spring force will be kx. You should take this. So basically, this is your x elongation. So spring force is kx. Kr root 3 minus 1. That's the first thing you need to find. Now, can you draw the FBD? Try. I'll give you a minute. Siddesh, you can't give the answer in terms of n, Ray. N we don't know.
So is the speed increasing or is the speed decreasing?
That I don't care. At this instant, what are the values? At this instant, speed is v. Why do you need that?
Sir, to find tangential acceleration.
नहीं चाहिए तुझे. अरे to find acceleration, you need forces, ना रे.
I mean, like the force which is greater will give the tangential acceleration. So
That doesn't matter. The sign will take care of it.
Okay, sir.
Why are you worried about that speed increasing or decreasing? The sign will take care of it. You don't worry. Then what's the next step, everyone? Free body diagram. See, I think if you get the free body diagram right, you got everything else. So this was the ring. So what are the forces? mg. That will be always down. Normal reaction will be in this direction. The spring force will be from this point, remember the spring force will be along the spring. That will be in this direction. I'll do one thing with this n. I'll draw like this. This is the normal reaction. This is your spring force kx. This is your center. This is 120 degrees. This is an isosceles triangle, so this is 30. This is 30. This is 60, so that will make 90 again. So this also will be 30. Hope you're getting the components. So now if you resolve the forces on the ring, you have normal reaction. We have kx cos 30. We have mg cos 30. And we have mg sin 30. And we have mg that's mkx cos kx sin 30. And since you're going in a circle, you'll also have a centripetal acceleration v square by r. So centripetal acceleration is the easiest one. I don't care about the forces. AC is v square by r. Done. Are you getting it? Now write the forces. Kx cos 30 plus mg cos 30 minus normal reaction will give you mass into centripetal acceleration. If you simplify this, you'll get n ka value from here. And you'll also have a tangential. I'll assume in this direction. The signs will take care, don't worry. So in the tangential direction, kx sin 30 minus mg sin 30. These two are fighting. They will provide your a tangential. So from here you get a tangential. Check. Any doubts on this? And you have to just substitute x ka value there. Any doubts on the steps here, everyone? If you see carefully, all we did was draw the FBD, isn't it? Clear na, Vedika? Any doubts on this? Utsa? Devanshi? Samyak? Devanshi, clear na?
Sir,
Arya.
in this second equation which you have written, you have assumed kx sin 30 is greater than.
Greater. If it is less, so 80 will be negative. NLM में
yes,
वही
sir.
करते हैं ना रे. Why you bother? Like you always assume
Okay,
whatever
okay.
you want. Science will take care.
Okay.
All clear with this? Next one. This is your top view. So what happens if you go with a car and you go very fast on a turn? Let's say we have a rough wall. Friction mu, the side view will look like this. This thing, recently I saw some video there. I think it's a Formula racing car or something. The driver, right, is going fast. I think he hits the wall. He actually drags on the surface of the wall. Anyone has seen that? So there's a thing like that. I think it is banned now, but he used that to win the race.
Yes, sir.
Yes.
Sir, he learned it from his brother's video game.
Where did I keep this? And then make it. Name. Interesting. Circular here. There. Look at this picture. So we have a wall like this. So you're coming with your car. You enter the block like, this is the block. So you're entering with speed V. And the wall is rough. And you start dragging on this wall. And then you come out. Now, because of the friction, this angle is theta. So when the block comes out here, because of the friction, you'll come out with a different speed. Let's say this is V and this is U. So you entered with speed U, you come out with speed V. So as this thing is dragging, you will observe the friction will be always like this, isn't it? The friction will keep dragging this thing on the backside like this, if you're dragging on the wall. So the same picture, and the floor is smooth. Smooth is the floor smooth, but the wall is rough. So we have a block here of mass m, which enters with speed u. It enters the curve, and finally, when it comes out with speed v. So from here to here, this angle is theta. I hope, is the scenario clear, everyone? A block enters a curve. Circular curve of radius r, right? And slides on that rough wall. Friction is mu. So it enters with u and leaves with v. Find v. The u is given, mu is given, theta is given.
Is theta also a given quantity?
Theta is also given.
Okay.
Anyone didn't understand the question or the picture, please ask me. If you got the question, picture, then it is great. Then go ahead. I'll give you 2 to 3 minutes. So the body will slow down because of the friction on the wall. The floor is not going to do anything. Everyone should try. And again, I keep telling you every time, definitely after every class, please make sure to solve each and every question in the class notes. Your class notes itself is a bunch of, big collection of questions. And after that, do solve your material. Simple target. try to solve 20 questions per day, 5 days a week, 100 questions per week. That's the target. Where to solve from? Solve from your classes material, solve from my material, DC Pandey or HCM. Choose any two materials. Don't try to do each and every book. Choose any two. Do them properly, thoroughly. And every week I'm conducting an exam. Write that. See where it went wrong and try to improve. You do this consistently over a span of 6-7 months, things will get much better. So that's how you do that. You do that work consistently. How to do this? Right, Siddesh, we have one answer. आर्या देखो ना तेरा स्पीड इंक्रीज हो रहा है गॉड You gained more speed than initial speed. You have created a system where you can get free energy. You are the pioneer of humanity. You have saved the world from energy crisis. We need you. You have solved the world's hunger problems. You will get a peace Nobel Peace Prize before Trump.
Before Trump means it's never gonna happen, sir. There we have two answers. Arya also got it. Others, anything else? Someone else also got it. Samyak, you're also the pioneer of energy. You have created free energy systems. Your speed is also more than the initial speed. See, one thing I'll tell you, physics that I have noticed in 11th and 12th physics, normal level physics also, you will never get e power plus into something. Because physics if you get something e power plus some quantity, meaning this value can blow off to infinity. In physics, we don't like infinities. You can't have infinite energy, you can't have infinite velocities. So 99.9%, if you get e power plus something, understand you forgot a minus sign somewhere. Just replace a minus sign, it becomes right. You will never get e power plus something in physics. Sir, you had given a question of friction due to pulley. That we had gotten e power plus.
वो rare है. That is the thing, na. So there the tension force is increasing, but eventually a physical limit it breaks. I know that is one there, but that's why I said 99.9. 100% कहाँ पे बोला मैंने?
Yeah, and we also had one question in J advance.
E power में plus में?
हाँ sir.
Send me once. I don't remember which one.
Sir, that same question, HC Verma का आगे वाला वाला. Sec का
Which one?
integration. Sir, the
That
rotating.
one. Yeah. OBA. But उसमें there's a 1 minus omega t term also. There are. Then I think let's make it 98% of the time. We'll change it. Let's see how to do this thing. So look at the forces first of all acting on the block. Let's take our wall here. This will. So when this block is moving here, what are the forces acting on this block? You have your own weight mg. You have your normal reaction from the ground. These are not important. You have a normal reaction from the wall, which is pushing you out. This is the end wall, which is pushing you out. The centrifugal force is pushing you into the wall, which is mv square by r. So basically that is the guy who is creating your normal reaction. And you have friction on the wall. And because of the friction on the wall, you'll get an A tangential. So the normal reaction on the wall is the centrifugal force mv square by r. Your friction on the wall is mu into n because it is slipping, which is mu into mv square by r. So this friction on the wall is providing your tangential acceleration m into at, which is mu mv square by r is equal to
mass into A tangential. M cancels. So we get A tangential is equal to mu V square by R. What is A tangential? Minus V dV by ds. Why minus? Because it's decelerating. If you see F and acceleration and this thing are in the opposite directions. One V cancels, you end up with minus dV by V is equal to mu ds by R. Integrate this on both the sides. This will become integral dV by V is equal to mu by R integral ds. And look at the distance here. This thing will travel distance of R theta. This will go from U to V and this will go from 0 to R theta, distance travel. This will become ln V, limits will go from U to V. This will become mu s by R, limits will go from 0 to R theta. This is ln V minus ln U is equal to minus mu R theta by R. This is ln V by U is equal to minus mu theta. V by mu is equal to e power minus mu theta. V is equal to U into e power minus mu theta. Check. That you have lost everyone. So technically speaking, you will never stop. Look at this thing. If theta tends to infinity, that means if this was a very huge curve, if even if it is 90 degrees, your speed will keep decreasing, but you will never stop. Clear with this? Any doubts on this? Great. Let's see one last one. We have a cylindrical rod, which is fixed at one end, and the whole setup is rotating with alpha. Alpha is what? Constant. It's a constant angular acceleration. Mean this rod is not going with constant speed; it is going faster and faster. So this is a cylindrical rod, and what you did, you took a ring and you placed it on this cylindrical rod at a distance r. Ring of mass m just fits over a cylindrical rod. So initially the system is at rest. The rod accelerates with this friction is mu. The rod rotates with gravity is also there. Constant angular acceleration, alpha. So question is, now tell me one thing, if I keep a ring like this and if you keep rotating, to give a simple analogy, think of like this. If you take a duster and put it on fan and if you switch on the fan, do you think the duster will remain there forever? For some time it will be there and then it will just push outside, isn't it? It will start sliding off. So something similar will happen. The ring will be there for some time and then it starts sliding. The ring will start coming out like this and flies out. So the question is, find the time when the ring slips. That's your first question. Second part, what if ring is replaced by a square frame? Then find time when it slips. Meaning, what do you mean by square frame? And the picture will look like this. Same picture, cylindrical rod, alpha, everything is same, but this time you're putting a square frame. How does this affect the problem? Same mass, same distance, everything is same. First, let's do the ring, then we'll think about the square. But is the story clear, everyone? If you put a ring or a square frame on a rod, right, and if you start rotating, at some point this will start skidding. Yeah, find the time when it starts slipping. Anyone didn't understand the scenario or the question? Anything you're not clear, please ask. What is happening? Again, do start with an FBD. Start with an FBD, you'll see something there. You have no idea what to do, always start with an FBD. Try. I'll give 2-3 minutes, then I'll show you. Okay, let's see. What is with this ring actually? Something else is happening here. Look at this. Like it's look at the the view from the rod perspective. Imagine if there is no rotation, right? How will this thing look like? Wish I had a ring. Yeah, I got something here. Look at my screen. So let's say if I have a rod like this, you can see the black pen, and let's say this is the ring. Now, can you see what is happening when I keep the ring here? If I don't rotate the ring is pushing it down. I think the black and black are becoming this much. There, look at this. Can you see what is this ring doing here? If I just make it hang like this, can you tell me how is the normal reaction? Isn't it up? The normal reaction is pushing up and mg is down. Okay? That is one. Suppose if the ring is rotating, then where do you think it will touch? Now see, if the ring is rotating like this, now can you see where it's touching? It is touching horizontally. You can see that. When you're rotating, you will touch horizontally. When you're hanging, you will touch vertically. That means if you have weight and if you're rotating together, then the force will be somewhere here, na, at a diagonally. You're getting it? So they won't. So the thing is, where do they touch? So if there is no rotation, the picture would have looked like this. So this is your rod, and your ring will look like this. Again, I'm exaggerating the figure a bit. So this will give a normal reaction Ny. This is responsible to balance your weight Mg. Suppose if there's only rotation and no gravity. Then the ring would look like this. This will be your Nx that is pushing you. Or you can say Nx is pushing like this. Making sense? That means if you have both of them together, if the rod rotates and you also have your gravity, so it's basically two circles touching each other. And we know two circles always touch at one single point. So they'll touch somewhere here. So you get a normal reaction in this direction. And this normal reaction will have two components, Nx and Ny. Is that making sense? So if you put a ring on a cylinder, there's only one point of contact. Since there's only one point of contact, there'll be only one normal reaction and one friction. And this one single normal reaction is balancing both your Nx and Ny. Any doubts on this page, everyone? Is the picture clear, everyone? Yeah.
Sir, I got your idea that the circle will touch at only one point, but wouldn't there be collection of normals if there is the ring is just fitting?
Just fit matlab hai, I know, and what you're saying, we are leaving little space for it to slide रहे, इतना भी tightly fit नहीं है.
Okay, means हमें integration नहीं करना पड़ेगा m omega square
वो
sin
सब
theta
नहीं
का.
करना है. Yeah, no. It is just like it just fits over. मतलब
Alright.
hey, अभी भी थोड़ा gap. If you exactly fit it, it won't slide only then.
Okay, so
You
it will
don't want to
touch.
get into that.
It's so
Single
fitted
point,
that
single
it will
point.
only one point only.
Yeah.
Okay, sir.
It's clear now, yeah. So we are just putting little loose actually. It is not इतना भी tight नहीं है. But everyone is clear with this picture. Now let's draw the free body diagram. Now see how many forces are there. You will clearly see this thing. So this is there. So our ring is here. So what are the forces? You have your Mg. You have normal reaction got two components, Ny. You have one normal reaction like this, Nx, which is tangential. You have your centrifugal force, m omega square r, and you have friction. Check. Total this many forces are there. And since you're going in a circle here, you'll also have a tangential, which is r alpha. And we know omega final is equal to omega initial plus alpha t. So omega will be omega initial is 0, and this is your omega. So what are these forces doing? So your Ny is balancing your Mg, and your Nx is actually providing the required tangential acceleration. So Ny minus Mg is 0. So Nx is providing your tangential acceleration. Nx will be mr alpha. So what is a normal reaction? Root over Nx square plus Ny square. So this was the headache. root over g square plus r square alpha square. Your normal reaction is not mg. That's your normal reaction. Who is balancing the centrifugal force? Friction, which is m omega square r, and friction is less than equal to mu into n. This is m omega square r less than equal to mu, n is m into root over g square plus r square alpha square. Mm will cancel. What is omega? Alpha square t square r is less than equal to mu into root over g square plus r square alpha square. Square on both the sides, alpha power 4 t power 4 r square mu square g square plus r square alpha square. These numbers are mu square by r square alpha power 4 g square plus r square alpha square to the power of 1 by 4. There, they will slide it this time. Is that clear, everyone? So the main catch of the problem is this: the ring will touch only at one point, and that point will be at an angle. So that normal reaction will provide two forces, nx and ny. Your ny is balancing weight, and your nx is making the ring rotate in a circle, tangential acceleration. So your normal reaction gets messed up. You can't take n as mg directly. And as the ring rotates faster and faster, omega keeps increasing. So eventually your centrifugal force will dominate friction and you'll drag out. Is this making sense? So what is the catch with a square then? So that was the second part of the question. If you replace this ring with a square, then what happens? Any ideas? Yeah, right, Arya. Anyone else? What do you guys think? If you put a square, what is the big deal? Ask yourself, if you put a cylinder inside that square, how many points of contact will be there? So now if you put this, and if you put the square frame, won't it look like this? There are 2 points of contact. So you'll get ny, you'll get nx. There are 2 normal reactions. That means there'll be 2 frictions. So how does that change the problem? Let's see what changes then. Same story. So if I draw the free body diagram, now look at the forces. mg, that was the same thing. ny, that is also same. nx, that is also same. Centrifugal force, that is also same. But now we have 2 frictions, fx, fy. And you're having a tangential acceleration. So now the problem is this: who is stopping centrifugal force? Fx plus fy. And what is fx plus fy? Mu into nx plus ny. Did you see the difference? So this nx will become m into r alpha, ny will become mg. This is n omega square r, which is alpha t whole square r. The difference is this, everyone. In the previous case, normal reaction is root over nx square plus ny square. In this case, normal reaction is nx plus ny, isn't it? Which will be bigger? Is a square plus b square ka root is big, or a plus b is big? A plus b is bigger, isn't it? You actually get more friction in the square ka frame. That means square will take more time to slip. So mm will cancel here. We get t is equal to mu by r alpha square, r alpha plus g whole to the power of half. There, your whole answer changes. Just because you change the shape. Are you clear with the difference? If you have 2 points of contact, you get 2 normal reactions, and the friction will be F1 plus F2. In the previous case, there's only 1 point of contact, so normal reaction is root over nx square plus ny square. and that messed up the whole friction ka value. Yeah.
So like I said earlier, if the spring was just fitting and we'll have to take the collection of normals then. So can you show the integration, please?
वो
How
नहीं कर
will-
सकते हैं, but can't you? You'll not be able to do that, right? You can only find the net force, na? The problem is we don't know with what force you are compressing and with what force it is sticking. So if it is just fitting, there'll be always only one point of contact actually.
Hmm.
Even if it is just fitting, we will say you're touching, but there's no normal reaction.
Okay.
There is no way to do that actually. Meaning, you could have actually asked something like this. If you had put an equilateral triangle, then what would have happened? That would be more messy. Then you get two normal reactions like this.
No, instead of integrating, I found the work done by the normal reaction.
Don't need that. Clear with this, everyone? There. So with that, we are done with the non-uniform circular motion. Now after this, we're still left with one more part called radius of curvature. And then I told you, right, we'll also do that Coriolis acceleration and all those problems. So that part is left. So I think we will take another maybe 3/4 of a class. We will wrap it up. So next class, when we do this, we will finish off this. And then after that, we'll start off with work power energy.